Good afternoon, everyone. I'd like to start by introducing myself. My name is Yao Ge. I am a student at the Nankai University. The theme of my presentation is Lucene-based block indexing technology on large email data. What I would like to do today is to illustrate how we build an email retrieval system by using Lucene and block indexing technology. I have broken my speech down into 4 parts. In the first part, I am going to introduce about our work's background and Lucene. In the next section, I will explain our system design scheme and implementation details. In part 3, some search and evaluation results will be shown. In the last part, I would like to give the conclusion and future directions. Now, let's turn to the part 1. As we all know, this is an information and internet plus area. It's difficult for users to get useful information from the massive data. The appearance of searching engine resolve this problem. In our work, we are given the large email dataset stored in relational database MySQL. Users hope to do full-text search on the email dataset. Emails have already been parsed based on sender, receiver, content, and so on. Each mail has a special field called batch, which is an 8-digit number such as 20170629. We aim to build a retrieval system which can meet users' searching requirements. I would like to emphasize the fact that the response time and the query accuracy of searching engine are mostly determined by the index structure. However, the index structure of traditional relational database is very simple and has a slow searching speed. It also lacks the core functionality for retrieving and analyzing the contents stored in database. It is hard to meet the requirements of our search engine. There are two things we have to consider. In the first place, the search engine needs to search a large amount of data that stored format is simple. Second, the demand of a search engine is to give an accurate response ordered by relevance within a short time for many query requests. Obviously, the index structure in the database system does not meet this need. We should build the efficient index before runtime. So, how to solve this challenge? We choose Lucene. Now that we have seen the background and reason we use Lucene, let's turn to the introduction of Lucene. Lucene is an open-source Java-based full-text search architecture. It provides a complete query engine, index engine, and part of the text analysis engine. Simple application programming interface makes it convenient for software developers to achieve full-text search function in the target system. Lucene has highly optimized inverted index structure, which can greatly improve the retrieval efficiency. Next, I will illustrate how Lucene works. It includes 4 steps. The first step is to build index documents after getting search source data. In this period, Lucene will convert other data formats into text, extract the index entries and related information from the word breaker. The second step is to save the index file in specified position. So we get our index file. The third step is to accept user's query and do searching according to index. The last step is to return present search results to user. So far, a complete retrieval system process has finished. Although Lucene has provided calling interfaces for building the index library and the retrieval mechanism, in practical application, it still has a problem should be noticed. The size of the index file is linearly increasing as the number of the emails needed to be indexed increased. Due to system primary requirement is to do interval filter for the specific files batch and then do keyword search. It seems not necessary to search the entire index file every time. Based on this fact, we split the gigabyte level index file into multiple small block index files according to the batch field. Then we only need to search on the index which satisfies the query range. The scheme of coexistence of the integrated index and block index is applied to our retrieval system. Well, let's now move on to the second part, which is, as I said earlier, system design theme and implementation details. The retrieval system has two kinds of users, common users and administrators. First of all, administrators send the index building request. The system will pass the request and build the integrated index and the block index for the data in MySQL. After finishing the index building, common users could launch the searching request according to personal needs. The system server will pass the request and decide which kind of index to use based on specific request, and then load the index files for searching and return the search results. Then, let's see the specific process of building index and searching. The first one is kernel classes and their transfer relations during building index. Class getParams is inherited from HTTP servlet, which uses the HTTP communication protocol. After its doPost function receives the request for index building, it will create an object of class indexThread and call the start method of indexThread to start the index building. The run method will first connect database and load all batch information. It will then create index file folder and name each index file using the corresponding batch name. At the same time, the index building log will be recorded into database by index log function. Since we got the email information from the database, the initialize method of the class mail index will be responsible for building two kinds of indexes. The kind of integrated index builds index for each field of the email, and there is only one index files folder. As for the block index, there are multiple folders. The name of the index files folder is the batch name, and the number of the index files folders equals the number of email batches. Since we have built index files, what we are going to do is dealing with users' searching need. Users send the post request to server using browser in the way of JSON. We still use class getParams to accept users' request. The doPost method receives the searching request and passes the JSON string to the getJSON object created. The parseJSON method of class getJSON will pass the JSON string, generate, and return the searching structure. After receiving the structure, get params would call different search methods for integrated index and block index according to the batch interval. The query mills distributed method will do searching on every index field within the interval, while the query mills integrated method just will do simple search on the whole index field. Both of two methods will call multiple paging query method of class mill query, which construct the searching object by using the Boolean query to do the OR operation on the two search objects. One is the query parser of the keywords, the other is the range query of the batch. And the getJSON function return data is responsible for returning the searching results. I have introduced how to build the two kinds of indexes and how to perform the searching process and returning the results. However, when to use which kind of index is not sure. Thus, we have done the searching evaluation. The next point I would like to show is how we do evaluation and its results. Well, let's think about what factors will affect search efficiency. Above all, the batch interval decides how many block index fields needed to be loaded into the disk. The interval bigger, the searching efficiency is slower. Second, the size of a block index field associates with the data amount needed to be loaded into memory. Finally, different keywords will result in different sizes of result size. All of this will affect the searching efficiency. Thus, we perform the experiments by varying parameters from these aspects. The first part is the effect of the size of index field to searching efficiency. We perform the searching evaluation on 200 batches. Table on the slide shows part of the searching results. We can see from the experimental results that block index is obviously better than integrated index. When we search on one batch, clearly, the smaller the index field, the more apparent difference between two methods. When the size of the index field is less than 1 MB, the searching efficiency of block index is 10 times better than integrated index. And as the increasing of the size of the index field, the advantage of block index is decreasing. The second part is the effect of the size of the batch interval. Referring to the first part, we can find when the batch interval is 1, the block index has significant advantages. However, as the batch interval increasing, the I/O cost of block index is increasing. So the assumption is there is a cross point that before this point, the block index is better than integrated index, while after this point, the integrated index is better than block index. We still perform the experiments on the same 200 batches. The partial results are shown in the table. We can see that block index is better than integrated index when batch interval is less than 10. However, the part close to 200 do not perform as expected. In our expectation, since the block index needs to load multiple index file folders to memory, the frequent I/O operation becomes the bottleneck. Thus, the searching efficiency should be worse than integrated index. However, as we have seen in the table, the block index performs close to or even better than integrated index in most cases. Since we do experiments on block index and integrated index respectively, it is possible that the system did not do the whole I/O operations in every searching. Thus, we perform experiments for block index and integrated index alternatively. We can see that in this case, the integrated index performs better than block index, so we should still use integrated index when the batch interval is large. The last part is the effect of the size of the resource set. Without going into details, I just want to point out that after we perform tests on the effect of different keywords, the results are similar to previous experiments. Thus, the cross point appears in 10 to 15. We can decide strategy according to this point. We can see from the experimental results, when the batch interval is less than 10, the searching efficiency of block index is better than the integrated index in most cases. However, when the batch interval is large, say approaching 200, the searching efficiency of integrated index is better than block index. When the batch interval is in the middle, the searching efficiency of the two methods are close. However, due to the uncertainty of searching requests, there could exist a great difference among the two continuous searching requests. Thus, to reduce the disk I/O operation, it is recommended to use integrated index. Moreover, considering a large batch will decrease the searching efficiency of block index, we could record the large batches in advance. When the searching requests touch on many those batches, we could use integrated index. I would like to summarize that Lucene has unbeatable searching efficiency compared to traditional relational database. After realizing the basic retrieval system, we further proposed two kinds of indexes to meet the need of fast search on specific batch interval. We also do searching evaluation to make sure how to choose index strategy. The coexistence of block index and integrated index has improved the searching efficiency. Of course, we could still improve in some aspects. Currently, we only use the batch interval to select different index methods. We could consider more factors for choosing the index methods. We use single machine in this work. However, when the data size is further increasing, we could try to deploy the system in a distributed manner. Finally, thank you for your attention.